This is question 2 of the 2015 electricity exam. I'll be starting with question 2A. So what we have here is we have a DC circuit with a little bit of internal resistance running at 9 volts, running just through, so it's charging up a capacitor, and then once it's fully charged, the circuit will stop flowing. At this instant, at this point in time, the capacitor has a voltage through it of 6.4 volts, and at this instant in time the current flowing through the circuit is 0.208 amps. Notice again all the numbers are given to us in 3SF. We'll also be given at the top dielectric constant of air is just 1, and that's also equal to the ER symbol, and we've got the permittivity of free space, which is just epsilon naught. Show that the internal resistance of a cell is 12.5 ohms. So there are two ways to go about this. The first way would just to notice that we have 9 volts coming out of the battery going round to the capacitor. If we subtracted off the voltage that the capacitor has currently got through it, we'd get the voltage flowing through this resistor, and then we could work out from that voltage using that current resistance of the resistor. But that would just demonstrate to you the answer, but that wouldn't actually demonstrate, that wouldn't show that the internal resistance is 12.5 volt ohms. So the way to do it with internal resistance, we know that V is equal to EMF is equal to V minus IR, where EMF is it's called the electromotive force, but it's really the actual current flowing in the circuit, the actual voltage I should say, flowing in the circuit, minus you take out the voltage that's used through the resistor. So this is our actual voltage that the capacitor, that the battery can actually put out by the time without the internal resistance factored in, and this is our internal resistance, and this is the current flowing through the circuit. So let's just rearrange for R to begin with. So we have E minus V is equal to IR. We've got a minus here as well. We'll put some brackets around this, cancel out that R, divide by R, and we'll just move that minus sign to the other side, and then substitute in the values. So our EMF flowing around the circuit is just 6.4 volts. So that's the voltage that's actually managing to get through the circuit. So that's 6.4 volts. 3SF again minus. So that's the EMF minus 9 volts. That's what the battery is actually putting it out. Divided by the current. That should be divided by I. Divided by the current, which is 0.208 amps, which is indeed equal, and we've got a minus sign in here, which is indeed equal to 12.5 ohms. Notice that again everything's in 3SF, so my answers and my values that I put into my calculator need to be in 3SF. Cool. And that formula isn't given to you in your formula sheet, so you need to know that off by heart. Question 1B. The capacitor has air between its plates, plate separation of 2.26 times 10 to the negative 4, so that's 0.2 macrometers or millimeters. Capacitance is 2.75 nanofarads or times 10 to the negative 9. What is the overlap area of the plate? So if we go to our resource booklet, we'll notice that. So that's capacitance for capacitors lined up in parallel. That's for them in series. This is I suppose the capacitor linking to the area of the plates divided by the voltage, and then we are got two constants in here as well: the permittivity of free space and the dielectric constant. So if we quickly write that down, C is equal to epsilon naught times A divided by the separation distance, and what it's asking for us is what is the overlap area of the plates. So essentially, if you have two capacitors stacked together, the only area that we care about is the area that's actually overlapping. This area right here, it doesn't mean anything because there's no electric field between them. So it's only the two plates with the electric field between. So we have, let's just rearrange for A first. So C times D divided by epsilon naught times dielectric constant is equal to A, and all we need to do now is just substitute in the values. So 2.75 times 10 to negative 9 farads times separation distance 2.6 times 10 to the negative 4 meters divided by epsilon naught, which is the permittivity of free space, 5 times 10 to the negative 12. I worry about putting the units in because I've got enough space, but as you can see up here, it's farads per meter squared because it's just a constant. And our dielectric constant, because it is air between the plates, it's just 1. And if we plug that into our calculator, it should spit out area is equal to 0.070 meters squared. And that's a pretty reasonable area for a capacitor. Anything more than a meter, that's a pretty ridiculous sort of capacitor, and it wouldn't make sense. Right. Recently in the news, a teenager claimed to have developed a supercapacitor as a way of rapidly charging a cell phone within 5 minutes. The actual circuit in the cell phone is complicated, but the use of the capacitor to supply energy to the charging unit can be modeled as a simple circuit. In the circuit shown, a capacitor with capacitance of 15 farads has been charged to 5 volts and is now discharged through a resistor which represents the charging unit. So this is our capacitor right here. Notice 3SF again, 15 farads. This will be the voltage across it, and it's at this stage it's at 5 volts. The maximum voltage it's at is 5 volts. That's a pretty hefty capacitor, but it's not unbelievable. It's something you find in a car stereo system. It would be, actually, it would. Right, use a graph to show that the resistance, the resistor is 4.5 ohms, and calculate the maximum current in the circuit. So this here is a decay graph. We have time down the bottom. Notice that it's just in seconds. Look out for microseconds, nanoseconds, so on and so forth. And this is our capacitor voltage in volts, if you can't quite read that. And like I said over the page, it was charged to 5 volts. So it starts at 5 volts. So first, let's just go to our formula sheet. We'll notice that time constant is the resistance times the capacitor. So that's basically, after one time constant, the voltage across the plates of the capacitor will decrease by 63%. So if it's sitting at 5 volts, 63% of 5 volts, I don't know what that is, but I'll figure that out. Right. So 5 volts, so first we'll write the time constant is equal to the resistance times capacitance. So V0, which is our original voltage, times, instead of, so if we're decreasing by 63%, that's just the same as timesing by 0.37, which is equal to 5 volts times 37%, but I'll put 37 is equal to 1.85 volts. So after, and this is after one time constant. So after one time constant's occurred, we're down to 1.85 volts. So let's just go onto our graph. Let's find 1.85 volts, which is just somewhere below 2 volts. And if I follow the line across, I can sort of see down to here, follow this down, it's 50, 60, 65, 66. So roughly we've elapsed 66 seconds. So our time constant is 66 seconds. Our capacitance is equal to 15 farads. So finding out our, finding out what our resistance should be time over the capacitance is equal to 66 divided by 15, which is indeed roughly equal to 4.5 ohms. Look at that. And we answer the question, show the resistance of the resistor is 4.5 ohms. Yes, we have, but calculate the maximum current in the circuit. Well, that's not too hard. V equals IR, but current is equal to voltage over resistance. The maximum voltage is 5 volts because it starts at 5 and just decreases from there exponentially. So that's just 5 divided by our resistance. We work that out, 4.5 ohms, which is indeed equal to, a calculator, 1.11 amps. Look at that. Okay, question D. One particular cell phone requires about 6 times 10 to the 5 joules of energy to fully charge. A supercapacitor of 400 farads, that is absolutely huge, could be used to charge a cell phone that requires 5 volts, the resistance of 4.5 ohms. Okay. Use calculations to decide whether the capacitor would fully charge the cell phone within 5 minutes. In this answer, you should calculate the time taken for the capacitor to become effectively discharged. Step 1, so that's what we do first. Let's just forget about everything else. So calculate the time taken for the capacitor to be effectively discharged. So effectively discharged, that just roughly means after 5 time constants, it is going to be effectively discharged. It's going to be it's going to have decreased by 99.98% of the original charge, or somewhere thereabouts. You can look that up, but I don't have time to go over that. So 5 time constants is equal to 5. I'll just put R. 5 times RC, which is equal to 5 times the resistance is still 4.5 ohms, but our capacitance is 400 farads, and that is equal to 9,000 seconds, which is also equal to 150 minutes, which is far longer than 5 minutes. Alright, look at that. Discuss whether the capacitor will release its energy within 5 minutes. Well, no, it's not. Far longer than 5 minutes, it's not. So let's just work out the energy first. So energy at a capacitor, E is equal to, let's go to our formula sheet. It's actually given to us. Where is it? Do they give it to us? There we go. It's up top. E equals half times QV. If we substitute in Q is equal to CV, we get E is equal to half, I'm just missing the half, CV squared, which is equal to half 400 times 5 squared, which is equal to 5,000 joules, or which is equal to 5 kilojoules, or yeah, I'll just leave it at that, or 5 times 10 to the 3 joules, either way. So that is how much energy is stored in the entire capacitor. So after it's fully discharged, that is how much energy it would have released. If we compare that to the energy needed, 6 times 10 to the 5 joules is nowhere near, that's way bigger than just 5 kilojoules. So compare the energy released by the capacitor that would be required. Spell that wrong. Energy released is far less than required. Just double check we've answered the question. Calculate the time taken for the capacitor to become fully discharged. Find time constants. I haven't fully explained that. Probably no, that's right. I explained that verbally. You should really write that down. And calculate energy released by the capacitor when discharging through the resistor. That's energy released. Compare it. Energy released is far less than the required. Cross that out. We need 6 times 10 to the 5 joules. I.e. 6 times 10 to the 5 is far greater than, what have we got? 5 times 10 to the 3 joules. There we go, made our comparison.